All right, let's get going, and we'll just pause when we have to pause and do the evaluations. Enough time's been wasted. All right. So let's talk about cascaded modulators. So what was the big problem with higher order modulators? Well, not linearity, right? Stability. You missed the quiz, man. All right. So what we're going to do here is we're going to use a cascade of um, lower first order and second order modulators to make a stable modulator. So this is a first order modulator here. So this terminal right here is V1 of Z times Z to the minus 1. And just for a sanity check, VZ of V1 of Z is equal to what? Vn Z to the minus 1 plus VQE times 1 minus Z to the minus 1. Anybody not agree with that? Okay, so then what I'm doing is I'm taking the difference between the input to the comparator and the output of the comparator, which by definition is the quantization noise. I'm going to send that to the next stage. We don't know how we do that, so because I'm doing it in this direction. This terminal here, V2 of Z, then becomes minus VQE1 of Z times Z to the minus 1 plus VQE of Z times 1 minus Z to the minus 1. Does everybody agree with that? So the input is minus VQE of Z. It's delayed to the output. And then this terminal here is this times 1 minus Z to the minus 1. Looking good? And so now if I add those two together, what I end up getting, and let's say let me just write it on a fresh sheet, actually. Still got a clip on that paper. What I end up getting for V out of Z is V in of, and then this is V in of Z to the minus 1 times Z to the minus 1. I should put this, that's that. So it'd be Z to the minus 2 plus Z to the minus 1 times 1 minus Z to the minus 1 times VQE1 of Z. And then that's plus 1 minus Z to the minus 1 times Z to the minus 1 minus VQE of Z. So what do you notice about these two terms? Yeah, they cancel. And then that's plus 1 minus Z to the minus 1 times VQE of Z times 1 minus Z to the minus 1, which if we take all of this and put it together, we get V in Z to the minus 2 times, or plus 1 minus Z to the minus 1 squared VQE of Z. Second order noise shaping. And this is called a 1-1 MASH, or a cascade of first order modulators, where this is multi what is it, the term again, MASH, multi-stage noise shaping MASH topology. But everybody gets the basic idea, right? So you cascade a 1-1 modulator. Well, I didn't come up with that acronym. That's what somebody else came up with. So that's a 1-1 modulator. So I wanted to briefly talk, before we talk about other modulators, about leakage. So you could, well, first off, let me ask this. Is there any imperfection in implementing these blocks? No, they're digital, right? So they're precise. It's just a delay of 1 bit and then just a differentiator. Okay, and so there's no imperfections there, but you might ask, well, what if this subtraction here is an imperfect? And I go through, and I'm not going to spend the time on it today, but I go through that and show that if you have leakage from the first stage doesn't precisely cancel. It's given by this equation right here. You get this unwanted term that's related to the gain not being precisely 1, and so that lowers your signal to noise ratio. But MASH topologies are still very popular for doing analog to digital conversion. All right, so, yeah, whatever. He said that one was the master. I don't think so. I think it doesn't matter. Anyhow, all right, so let's talk about a third order. You can imagine what a third order is, but it's a cascade of first orders. And let's go through that real quick. And what we have is, so I'm just going to go, now that you know what's what. So I'll just write the output directly. V out of Z is equal to Z to the minus 2 times, you missed the quiz, man. Z to the minus 2 times Z to the minus 1 Vn of Z plus VQE of Z times 1 minus Z to the minus 1 plus Z to the minus 1 times 1 minus Z to the minus 1 times Z to the minus 1 VQE of Z plus, this would be 1 VQE2 of Z times 1 minus Z to the minus 1. And last but not least, Z to the 1 minus Z to the minus 1 squared times times plus VQE of 2 of Z, and then that's times Z to the minus 1 VQ, oops, I already got that, plus VQE3 of Z times 1 minus Z to the minus 1. Anyway, you get the basic idea, and what you end up getting is Vn of Z, Z to the minus 3 times 1 minus Z to the minus 1 cubed, VQE. And so again, the problem is that you get leakage from one state to the next. Does everybody get the basic idea? So this is a 1-1-1 MASH. So what does that correspond to? What's that? Three first order modulators, right? So you might ask, well, can I apply that same technique to a second order modulator followed by a first order? And the answer is yes. And so if you look at that, and let's go through and feel the pain on this one. So you all help me since you know. What do I write the output as? V out of Z is equal to Vn of Z times what? Z to the minus 2. Then plus Z to the minus 1 times 1 minus Z to the minus 1 squared, VQE1 of Z. Anybody not follow this point right here? Why is it Vn times Z to the minus 2? Yeah, because it's, yeah, so there's a delay there, then there's a delay for the forward path of the modulator, and then you get second order noise shaping because this is a 2-1 topology, and then that's delayed here. And then that's added to, so that's 1 minus z to the minus 1 squared times z to the minus 1 times minus VQE of z, which is plus VQE 2 times, let's go for the gusto, 1 minus z to the minus 1 cubed. So what do I know about the middle terms? They go bye-bye unless there's leakage, and so I get Vn of z times z to the minus 2 plus VQE of z times 1 minus z to the minus 1 cubed. Any questions on that? So if I gave you this as a quiz, I said derive the transfer function of this 2-1 MASH on Wednesday, no one would be challenged, right? Question? Yeah, because so we're assuming we get the negative here and then these two cancel. So this basically what you're doing with this is you're digitizing the quantization noise from the first stage and then subtracting it from itself in the output. So you digitize it and then you feed it back here and subtract it. Okay, so last but not least, let's talk about how we implement this block here, because that's the only thing. If you look at this, you all at this point know how to implement this in switch capacitors. You know how to implement this in switch capacitors. That's a register, that's a differentiator, so you know how to take care of that. So the question is, how do I implement this? And I'll show you right here. So I want to just focus. Notice I have this signal coming in, this signal coming into a differencer. The output there goes to this signal here, which is the feedback. So I want to talk about implementing these. Does everybody follow? Okay, so we'll go look at that on the next page, which is seen right here. And there's what we talked about. We have the two adders and how we're taking this goes to the integrator. So you notice that here what I'm doing is, instead of showing two adders, I'm showing a single adder with 3 inputs. Why would I want to do that? Well, yeah, I can use a switch capacitor with 3 inputs and 1 op amp to implement this, right? And get the same transfer function, and that's what I show on the following page, just right here. And let's just see if we can figure out what's going on here. So this would be 6. So just tell me, I don't want you to do math or timing diagrams or anything. Just tell me intuitively, how would you find out what the transfer function is? Where would you start? I mean, just look in the book quickly. You want to quickly decide where the transfer function is. Yeah, I'd go to chapter 2. And then I'd pull up those charts and I'd say, oh, I don't have any with 3 inputs, but wait a sec, I can use superposition. And so if I look at the first one here, the V1 and the V2 going into the switch capacitor, that's just O1 and V2. Does everybody see that? It's the same exact thing. And then I can come down here and go, oh, well, if I have 2 inputs and I don't have a switch on the output, which is the same as having outputs connected to V2, so if there's no switch here or the outputs are connected to Phi2, I get this transfer function here. And then if I say, well, how do I get the next part of it? It's just superposition. It would just be with the 1 input fed back, which would only be V2. It'd be the first part, and the output's connected here for V2 to get my subtraction. And if you go through the math, you see that there's a z to the minus 1/2, but the way, remember, we clock the comparator, it gives us a z to the minus 1 in the numerator of the transfer function. Did I lose anybody on that last one? So let me refresh your memory. Did I? I'm sure I did, unless your brain is like a steel trap. I'll just point you to the appropriate place. Yeah, steel trap, everything comes in and nothing comes out. Let's go to the second order modulator and look at this discussion right here, where we've pushed that half clock cycle delay out to get the second order implementation. So we just assume that the first integrator is 1 minus e to the minus 1, and the input arrives a half clock cycle earlier. All right, does anybody have any questions about any of that? So does everybody understand what a cascaded modulator is? So if you were asked, what's a cascaded modulator, you would say, oh, it's a cascade of lower order stages. What's the purpose of using cascaded modulators? Better stability. You're using stable first and second order feedback loops. There's no feedback between like a 2-1. It's around the 2 and it's a 1. You're just feeding something forward. So it gives you better stability. Are there any questions on any of that? All right, so let's pause here and convert that